All right, so I want to welcome everyone to the interview today that we're doing with Dr. Zach Pennington. Dr. Zach Pennington completed his PhD at UCLA, went on to do his postdoc at the Icahn School of Medicine at Mount Sinai, and he'll be joining us here at UBC come January as an assistant professor in the Department of Psychology and as a member of the Djavad Mowafaghian Centre for Brain Health. So thank you for being with us here today, Zach. And I want to just first, yeah, for sure. And first, maybe if you could just take us through your background and where you studied, kind of your research that you were doing at these universities, and what eventually brought you here to UBC.
Yeah, happy to. So I actually, going back to my undergraduate days, I was a psychology major and have always had sort of psychology at the core of my research, and initially was really interested in becoming a clinical psychologist, but then I took a behavioral neuroscience class and was just completely captivated and realized that there was a lot of potential for advancing mental health by a better understanding of neurobiological causes of mental health conditions. And so I jumped into a lab at UCLA and really just fell in love with being in the lab. You know, the questions, the camaraderie, tinkering with things. I'm a big tinkerer. I like doing playing with different toys. And so I ended up doing my PhD in psychology and behavioral neuroscience at UCLA in the lab of Michael Fanslow. And there I studied interactions between opioid use and stress, showing actually that the chronic use of opioids is able to lead to a lasting increase in stress sensitivity. And we were able to sort out some changes in the amygdala that correlate with these changes in heightened stress sensitivity in mice. And so that was sort of the basis of my doctoral research. And then for my postdoc, I really wanted to integrate various computational tools and also imaging techniques into my background in psychology and behavioral neuroscience. So joined the lab of Denise Kai here at Mount Sinai, where I am now until January. And there I've continued to study stress, really focusing on individual variation in stress responses. So we know that, you know, not everyone experiences stress in the same way. And so been trying to figure out what are the differences in neural circuitry that really support these individual differences in stress responses. So to do that, been utilizing a lot of techniques like imaging with miniature microscopes. So what this allows you to do is image up to hundreds of neurons in the brain simultaneously across long periods of time. So we can relate neural activity to behavior, and then we can causally test the contributions of these neurons to behavior with things like optogenetics, chemogenetics, other ways that we can manipulate neural circuitry. And so the result of my postdoc work is we identified a novel hypothalamic brain region, which seems to regulate individual vulnerability to stress sensitivity. And so now I'm going to be starting my own lab at UBC, which I'm super excited for. You know, I joined UBC because it just seemed like the most vibrant community, and there were a lot of people to collaborate with, and Vancouver is beautiful. I love food, and Vancouver has an amazing food scene, so I'm excited to be coming there for that. And you know, my lab will continue to be focused on the neural circuits that regulate stress, how these circuits are sort of altered in conditions like post-traumatic stress disorder, utilizing a range of techniques that includes things like imaging the brain in freely behaving rodents with miniature microscopes, manipulating neural activity with things like optogenetics, and also utilizing approaches that allow us to capture cells of interest, so we can explore, what is molecularly different in, let's say, stress vulnerable animals compared to animals that are resilient to stress.
Wow. Yeah. Sounds like you've had quite the extensive background in all these techniques, and really excited to bring them here to UBC and kind of get all that working in your lab. I want to ask you next, like kind of diving in a little bit more into some of that research. You mentioned this this hypothalamic nucleus, the anterior hypothalamic nucleus, and the research that you did in kind of how it encodes the valence of those stressors, and kind of bring that information, gating that information from the amygdala. Maybe if you could dive in a little bit further into kind of your work there and provide maybe just an overall summary of what you found.
Yeah, sure. So, like I mentioned, I'm interested in understanding individual variation in stress responses. And one of the things we know in humans really governs this individual variation is the prior experience of stress. And we see a similar phenomena in mice, where mice that were previously stress exposed show potentiated responses to future stress. And utilizing a whole brain unbiased approach where we can image immediate early genes across the entire brain, we identified this nucleus, the anterior hypothalamic nucleus, which shows heightened activation in stress vulnerable animals. And this nucleus is super interesting for a few reasons. The first of which is that it's highly interconnected with known stress regions like the amygdala, the hippocampus, and that puts it in this nice position to sort of regulate stress activity. But the other thing is that the hypothalamus in general has a number of unique peptides and markers that make it sort of an ideal candidate for pharmacological intervention. So if you're thinking about developing a treatment, you want something that has a great deal of specificity, so you'll have fewer side effects. So I started exploring this nucleus, and what we found is, as you mentioned, its activity seems to encode the intensity of stressors or how their valence. So the more negative something is, the stronger this nucleus responds. And we find that in previously stressed animals, this encoding is altered. And moreover, what we can do is show that if we sort of promote this nucleus's activity, we can promote heightened stress responses, and we can also attenuate stress responses by dampening this nucleus's activity. And then we've gone on to show, utilizing a number of sort of circuit approaches, that, as you mentioned, this nucleus receives input from the amygdala about sort of stressor intensity, and it seems to modulate what the amygdala is sort of saying about how negative things are in the environment. So perhaps by targeting this nucleus, we could sort of tamp down stress responses and make things a little less severe. So if we're thinking about potential implications for a condition like post-traumatic stress disorder, as new sort of cues come up that are reminders, maybe we could target this anterior hypothalamic nucleus to sort of take the edge off.
Obviously, and do you have some ideas of how you would target this nucleus, and is that a kind of a direction that you want to go with your lab here?
Yeah, this is exactly what we're really interested in doing. And so we've shown that broadly this nucleus is related to stress vulnerability, and specifically GABAergic neurons, but these neurons make up about 90% of the cells in this nucleus. But we know that only a subpopulation is really activated in response to stress. And so what my lab's going to be doing is utilizing approaches that enable us to hone in on, is there a specific cell type within this brain region that we might be able to target. And to do this, what we're going to be the approach we're going to be taking is utilizing these methods that allow you to tag the activity or tag neurons that are active at very specific time points. So we can ask, is there a population of cells that's reliably activated by stress? And then utilize approaches to extract those cells and figure out, do they have some sort of marker that could allow us to target them?
Very interesting. Well, it sounds like super promising research, and I mean, I feel like that's a pretty wide open field in terms of kind of modulating those responses for PTSD and the different implications that you mentioned, and kind of going along in a similar vein, the research that you did on fear memory. Maybe you could tell us a little bit about kind of the role of the basolateral amygdala and the ventral hippocampus, and kind of the independent effects that you see from each of those brain regions.
Yeah, certainly. So oftentimes when we think about the lasting impacts of stress, especially in the context of disease, so maybe if we're thinking about post-traumatic stress disorder, where an individual suffers a trauma, and then some of those individuals go on to develop a range of symptoms, so flashbacks, anxiety, hypervigilance, depression, these sorts of things. These changes that we see in symptoms are frequently attributed to a particular type of memory called associative memory. So these are the types of memories for cues that are sort of been associated with a stressful experience. So you might think of cues that were present at the time of the trauma. And this is the paradigm that we have, right? That if we were able to reduce the influence these cues have over an individual, we'd be able to lessen or treat their symptoms. But there's evidence to suggest that you could actually get rid of the associative memory for a stressful experience, so and still have other symptoms like anxiety. So in another paper that from my postdoc, what we found is you can give animals a stressor, and then you can, just after that stressor, you can block protein synthesis in the amygdala. And the amygdala is known to be really important for associative memories. And so you give them the stressor, you give them this protein synthesis inhibitor in the amygdala, and then a week later, you bring them back to that environment where they got this stressor, and it's like they don't care at all. But what you find is that if you then test them in an anxiety assay, what you find is that they're still equally stressed compared to an animal that received, or anxious compared to an animal that got that stressor but no protein synthesis inhibitor. And so what that really shows is that you can block the associative memory and they're still anxious. Something very different is seen when you block protein synthesis in the ventral hippocampus. And there you find that if you block stress-induced protein synthesis in the ventral hippocampus, it does in fact block that anxiety-like behavior in mice, suggesting that you have sort of different phenotypes that result from stress, and there are different neural circuitries that support these different changes. And one of the things that my lab is going to be diving into is figuring out at a sort of finer level what supports them.
Wow, so it really sounds like kind of you need a multifaceted approach to kind of combat this increased sensitivity following stressful experience. I guess we see that kind of those would it be engrams that are encoded in several places, and kind of you respond to it in different ways. So it's super interesting work, and I want to ask you, kind of being an expert in this field, I mean, lots of times, this is more of like a lifestyle type question. I mean, lots of times you can't really control if there's a stressful situation in your life. And I mean, it is a little bit like dismal to hear that kind of if that happens, then you're more susceptible to stress in the future. Is there ways that we know that we can kind of become more robust to stressful experiences?
Yeah, definitely. I mean, I think sleep is a big one, and the relationship between sleep and stress. So making sure one is well rested, otherwise taking good care of yourself. Social interactions are one of the greatest buffers against just about every psychological and physical illness. So I think those are the big things that jump out for me is, sleeping well, taking care of yourself, having a strong social support network to lean on. Those things all sort of buffer against the impact of stress.
Okay, so all the classic things that we know we're supposed to do, but obviously when you're in the midst of a stressful situation, it can be hard. You can have insomnia, or maybe it's hard to reach out to friends and kind of just get out and do things.
That is the rub. Yes.
Yeah, for sure. Well, thank you for expanding on that. And I also saw that you like to kind of create these open source software tools. Like I was looking at the EasyTrack tool that you made, and maybe you could speak a little bit on some of the tools you've made and the importance that you think of these kind of open source software tools that can help other scientists to achieve their goals.
Yeah, I mean, my interest in open source software has really just stemmed from my love, as I mentioned earlier, for tinkering and figuring things out. And when you get into the lab and you're working with equipment, and it's you could sort of just trust that it's going to work the way it's supposed to, or you could really want to fundamentally understand how that works. And the other thing is, I think there's a lot of equipment and tools out there that are really expensive, and you go, I don't have the money for that, and I don't have the resources for it. So can I just build it myself? And I started playing with these ideas, and then found that there's, this whole community of people who like tinkering and like building things themselves, and it's all free. And I think that it's just there's this incredible ethos embedded in that. I'm also, as an aside, really interested in DIY punk rock and punk rock bands that they put out all their own records and whatnot. So I think when I saw that in science, it's like, oh, I want to be a part of that. And so there are a few things that I've gotten involved in. One is with open source behavioral tracking. So one of the things that's sort of central to a lot of neuroscience, from molecular to systems neuroscience, is if we want to relate, whether it's neural activity or some, molecular change to behavior, we want to record and measure behavior. And there are a number of, and preferably you don't want to score it by hand because it's tedious and not fun work. And there's software available, but it was super expensive. And so I started just thinking, oh, could I do this in Python? And so that was the origins for a software I wrote called EasyTrack. And there's just been a huge response. It's now being used across 6 continents, which is wild. Wow. And I get emails from people, in whether it's South America or Africa, thanking me for this simple tool. I mean, it's not terribly fancy. It's not using the crazy machine learning algorithm, but it's incredibly useful and fast, and it operates across all operating systems, and it doesn't require a fancy computer. And so these individuals who don't have the resources that I'm lucky enough to have in the United States, where science is very well funded, and I mean even Canada is quite well funded. compared to most places in the world. And so, being able to do that has just been sort of a joy. And then once you start, getting positive feedback about it, it's like, oh, it just pushes me to continue on. So, the previous version of EasyTrack that we developed is really, it's based entirely on, like, you acquire a video and then you score. But now my own lab's going to be developing a version which actually does everything in real time. So you can record an animal, track its position in real time, and then you can actually interface with these little inexpensive Arduino devices, which allow you to control output. So you could say, turn on, a tone or a laser in response to the animal doing a particular action. Wow. So that's something that I have going. And then, I've also been very involved in a type of microscopy called miniscope imaging, which allows us to record neural activity in freely behaving animals. And you're actually taking these videos across time, and there's this question about, how do you take those videos and extract where neurons are and define what their neural activity patterns are? And so I've contributed to software that's enabled us to do that in an open source manner, and also utilizing very little computer resources. So previous things, like you needed a computer with 120 gigabytes of RAM or something like that, and now you can do it with 16. And so by sort of making things open and really accessible and useful, you can have a big impact on the scientific community, and just really, I think, increase equity in science too, by making it accessible to all.
Totally. Oh man. Yeah. Even just you saying, like, people using it all across the world and reaching out to you, that must be such an amazing feeling. And really lifting up yourself by lifting up everyone else too. So yeah, thank you for doing that. And I'm sure many people at UBC have probably used your tools as well. And so yeah, I mean, and kind of looking towards the future now, when you come here in January and you're going to be setting up your own lab, I want to hear from you. What would you say, if you could give me kind of top 3 directions that you're looking to go? I know kind of directions change over the years, but kind of what you envision yourself starting here doing.
Yeah, definitely. So a very big angle for my own lab's research will be, identifying cell types within the hypothalamus that regulate stress vulnerability, and seeing, can we identify biomarkers that might be useful in treatment of anxiety disorders, PTSD. Another big angle for my research is to understand how stressful memories sort of evolve over time. And so the sort of dominant view has been that you have a subset of cells in a particular brain region that kind of maintain a memory over time, but there's also data suggesting that this isn't the case, and that how memories are represented in the nervous system change as a function of time. And so that's something that my lab's going to be really actively pursuing. And thirdly, we'll be really sort of geared towards tool development, various open source tools. So I mentioned, EasyTrack and other sort of computer software for the analysis of various electrophysiology data and miniscope imaging data.
Very cool. I'm very excited. Maybe like 3 years down the line, look back on this video and see all the stuff you've been doing here at UBC, and kind of see everything that you accomplished. It'll be really cool to kind of go back and see that. And I also want to ask you, so I know that you're probably sorry, just getting a call there, but I know that you're probably trying to fill up your lab and look for students, and we have hundreds of really talented, bright students here in the program. And I want to ask you, kind of more on a student focus, what are you looking for in your grad students, both in terms of expertise, but also in terms of kind of the culture and fit that you want to make for your lab?
Just to clarify your question, graduate students or undergraduates?
For graduate students who will be starting, like, let's say, their masters.
Oh, okay, yeah, sure. I mean, I think for me, the biggest thing for people interested in graduate school is really having just a lot of passion and being a go-getter and being excited. You know, for me, I think it's good to have, you know, experience, some level of experience in a lab, and that could be in a variety of places, just knowing that you like and being in the lab. But you know, I kind of expect that any graduate student starting off is going to be sort of learning everything from scratch, and the main thing is like being excited about that learning process. So no big requirements, just like you know, the biggest thing I think for me is wanting to be on a team, you know, like being excited, liking to work with other people, liking to collaborate, sort of that. It's more the attitude than any specific experience that one has had in the past.
Totally. Yeah, I mean, a lot of students might probably be interested after hearing this and in the stuff that you're doing. So you heard it from Dr. Pennington, what he's looking for in a student. And I mean, that's all the questions that I have for you today. So I really want to thank you again for joining today. It was a pleasure to hear from you and to learn about the research that you've been doing and all the expertise and things that you plan to do here at UBC. I'm really looking forward to seeing everything that your lab accomplishes in the next few years. And yeah, it's a pleasure to speak with you today.
Well, thank you so much for giving me the opportunity. It's been great talking with you, Tom.
Yeah, thank you so much. And yeah, enjoy the last few months, and we'll see you here soon in January.